Welcome to the lecture series on numerical methods. So, now we are discussing about interpolation in various polynomials. So, last lecture we have discussed about these errors occurring in a Newton's forward difference formula, backward difference formula, and the general error terms what is occurring in polynomials. So, today we will discuss about or in this lecture we will just discuss about various examples associated with this Newton's forward difference formula or backward difference formula. So, if we will just discuss this example, we have to consider certain finite difference points which should be exist at equal spacings to get the solutions here. So, first example, if you will just consider here is a population model that is given in census in 10 years. Suppose we will just consider a problem that first example, a population is given for 5 years here. So, if you are just writing this problem, that is year as x and population as y here in 1000, that is suppose in 1891 the population size is 46,000 and 1901 the population size is like 66,000 and 1911 the population size is 81,000, 1921 the population size is 93,000 and in 1931 the population size is like 101,000. So, it is asked to find this population size for the year 1895. Find the population size in the year 1895. Since if you will just see that this population level is asked in the year 1895, which is existing at the beginning of the table. This means that 1895 will lies between 1891 to 1901 here. So, that is why we can use Newton's forward difference formula to evaluate this population size at this level here. And for that, first we will just construct the table, and from there itself we can collect the data, and then we can use the formula to evaluate this population size in the year 1895 here. So, if we will just prepare this table, we can just write in a tabular form here. First one is a year x, then the population size, that is in the form of y here. So, year is given as 1891, 1901, 1911, 1921, 1931, and the population sizes are like 46, 66, 81, 93, 101 here. And first difference, if you will just calculate here del y, 66 minus 46, that will just give you 20 here, and next difference 81 minus 66, this will just give you 15 here, 93 minus 81, that will just give you 12 here, and 101 minus 93, that will just give you 8 here. And for the second differences, if you will just compute here, that is in the form of del square y here. So, this is minus 5 here, then minus 3 here, then minus 4 here. If you will just go for third differences here, that is 2 here, then 1 here. So, sorry, this is a minus 1 here, minus 4, so this is plus 3. So, then the final differences, it is del 4y, so it will just take like minus 3 here. And if we are just seeing here, so the final value will be approaches towards the beginning of the table. So, that is why we can just consider these tabular values are in this form here. This means that if you will just use this formulation for Newton's forward difference formula, always this point is shifting towards the beginning of the table. So, that is why we can just consider the upper part of the tabular values for the computation here. And we have signified that one in a like a red color symbols in the data in the slides. So, if you just write the formula here, yp can be written in the form of y0 plus p delta of y0 p into p minus 1 by factorial 2 del square of y0 p into p minus 1 into p minus 2 by factorial 3 del q of y0 plus p into p minus 1 into p minus 2 into p minus 3 by 4 factorial del fourth of y0. Since your tabular values is existing up to fourth order difference here, so we can just consider this expansion up to fourth order term there. So, if we want to compute p first, since the year it is asked to find in the year 1895 here. So, first we have to find the value of p here. So, if you will just see the spacing here, the spacing is 10 here, and usually the formula is written as xp equals to x0 plus ph, or the data which is asked to find, which can be represented in the form of x here, and which can be written as x0 plus ph, and x0 is denoted as 1891 here, and h is 10 here. So, we can just compute, that is our xp value or the year which we have to compute, that is 1895 here. So, from these 3 data points, this is 10. So, from these 3 data points we can compute p as x minus x0 by h here. So, which can be written as 1895 minus 1891 by 10 here. So, this can be, the computed value will be 0.4. So, if you will just see here, p value should be lies between 0 and 1 for the application of Newton's forward difference formula. So, that condition is satisfied here, since p value is lies between 0 and 1 here. So, next, if we can just use this formula here, since p value is known to us, y0 value is this value here, and del y0 value is this one here, then del square y0 value is this one here, then del q y0 value is this one here, and del fourth y0 value is known to us here, and p value is 0.4 here, and all other values are known to us. So, now we can just compute what is the population size in the year 1895 here. So, if we will just go for the computation of this formula here, I can just write that one as in the form, that is y of 1895, this equals to first value is 46 here, 46 plus you can just write p value there, p delta of y0. So, I can write here y of 1895, this equals to y0 is 46 here plus p value is 0.4 here into del of y0 is 20 plus p value is 0.4 here. So, 0.4 minus 1 here by 2 factorial del square of y0 value is minus 5 here plus p minus 1 p minus 2 by 3 factorial into the last tabular value here is a 2 here plus your last value here 0.4, 0.4 minus 1, 0.4 minus 2, 0.4 minus 3 divided by 4 factorial into your last tabular value here minus 3, and the final answer it will just come as 85 thousandths. So, if you will just see here the population sizes, whatever it is just given here, this should be lies between 46 and 66 here. So, that is why this population size is accurate in order of this increment of the values in the preceding years here. So, if we will just go for a backward difference formula here, since all of these values are known to us, then we can just use this backward difference formula if the value is asked to compute at the end of the table. In the second question, it is asked that estimate the population for the year 1925 here. Since if the question is asked that estimate the population size for the year 1925, so 1925 if you will see, so this is just existing at the lower end of the table here. So, that is why we can use Newton's backward difference formula for the computation of the value or to find this population size for the year 1925 here. So, if we can just use these tabular values here, then we can write this backward difference formula as y of x as y0 plus p nabla of y0 p into p plus 1 by factorial 2 nabla square of y0 p into p plus 1 into p plus 2 by 3 factorial nabla q of y0 here plus p into p plus 1 into p plus 2 into p plus 3 by 4 factorial nabla to the power 4 of y0 here. So, now we have to first compute p according to the backward difference formula, then we will just go for this backward difference tabular values, and we can just put that values to obtain the population size for this year 1925 here. So, if you will just show this p value here, so p can be written as your x equals to x naught plus p is here. So, if you will just consider x naught equals to 1931 here, your x value is asked at 1925 here. So, p value can be computed as minus 0.6 here, where p is lying between minus 1 to 0 here. Hence, we can use Newton's backward difference formula, since the basic definition is that if p lies between 0 and minus 1, we can use Newton's backward difference formula to compute the tabular values at the end of the table. So, that is why p is just giving you the value that is as minus 0.6, which is lying between 0 and minus 1. So, that is why we can use backward difference formula there. And now we can just put these values, y0 value is starting here. So, that is why your x0 value can be considered as 1931 here, x of minus 1 value can be considered as 1921 here, x of minus 2 value can be considered as 1911 here, x of minus 3 can be considered as 1901 here, x of minus 4 can be considered as this value here. And the relative values we can just use 101, 8, minus 4, minus 1 and minus 3 there. So, if you will just write in a complete tabular form here, so that we can just write as, so y of 1925. So, first value is a y0 value here 101. So, plus minus 0.6 into 8 plus p into p plus 1 divided by 2 factorial nabla square. So, that value is a minus 4 here plus minus 0.6 plus 1 minus 0.6 plus 2 divided by 3 factorial, and this value is a minus 1 here plus minus 0.6 minus 0.6 plus 1 minus 0.6 plus 2 minus 0.6 plus 3 divided by 4 factorial into last value, that is minus 3 here, and the final population size is 96.8368 here. And obviously if you will just truncate this one up to 2 terms here, we can just write this one as 96,84,000. So next we will just go for extrapolation, since sometimes we are just finding that if the value is existing outside the table, so that is basically called your extrapolation. The process of finding the values outside the table, even if all of these tabular values are given, so by considering all this data which are existing on the tabular values, we can just find out the preceding or succeeding values by considering this overall data. Either it can be a future data or it can be a past data. So that is basically called extrapolation. If the value is computed inside the table, that is basically called interpolation here. And if you will just consider, for example, that if a value is asked to compute outside the tabular values, then it is called extrapolation, and we can use an example to find this extrapolated value here. So if the question is asked, suppose find the cubic polynomial which takes the values like y of 0 equals to 1, y of 1 equals to 0, y of 2 equals to 1, and y of 3 equals to 10 here, and it is asked to obtain what is the value of y of 4 here. Since 3 or 4 preceding values are known to us here, we can just use this extrapolation method to evaluate the value at the point 4 there itself. So if you will just write this difference table here, so this difference table can be written in the form, since x0 or xi datas, then corresponding yi datas. So your x0 value is 0 here, then 1, then 2, then 3, and yi values are like 1, 0, 1 and 10 here. So if you will just find this forward difference tabular values here, we can just write del of yi, del square yi and del q of yi here. So if you will just consider this difference, first difference is a minus 1 here, second difference is 1 here, third difference is 9 here, and the second difference if you will just see here, that is 2 here, then this is 8 here, and last tabular value is 6 here. And if you will just see here the spacing, that is h can be defined as xi minus 1, and it can be obviously your value is 1 here, and it is asked to compute the value at x0 equals to 4 here. So if we can just write here x equals to x0 plus ph here, and x0 as 0 here, since the value we have to compute that is in the form of x0 plus ph here, and x0 is 0, it is just given. So that is why we can just write your pH. So x equals to x0 means we can just write this one as x equals to p there, x equals to x0 plus ph here. So that is why we can just write this one as x0 is 0. So that is why x0 plus ph here. So first part, if this is 0 here, so 0 plus ph is this one, hence we can just write here x as p here. So if we want to compute this value at p equals to x here, this means that h equals to 1, first it is just given. I want to clear these things here. Since x is asked to compute, so x equals to x0 plus ph here, and h is 1, so we can just write x0 equals to 0 here. So that is why x equals to p here. So if h equals to 1 and p equals to x here, we can just obtain this function y of x in the form of a polynomial that can be expressed in the form of x here. Since first value, if you will just consider here y0 as 1 here, plus p is expressed as x here. So, p delta of y0, that is a -1 here, plus p into p minus 1 and by 2 factorial into next tabular value, that is 2 here, plus x into x minus 1 into x minus 2 by 3 factorial into last tabular value, that is 6 here. So, which can be expressed in the form of here x to the power 3 minus 2x square plus 1 here, which is a polynomial. And if we want to find the value of y at 4 here, we can just write 4 to the power 3 minus 2 into 4 square plus 1 here. So, it can be written as 33. So, next we will just go for the central difference table. Now, we can just discuss about central difference approximations. So, if sometimes the value is asked to compute at the middle of the table, then you can use this central difference approximations. So, basically the central difference approximations includes Gauss forward difference formula, Gauss backward difference formula, and Bessel's formula and Stalling's formula. So, in the central difference table, if you will just use Gauss backward difference formula, so the p value should lies between -half to 1, and if you will just use this forward difference formula, then the p value should lies between 0 and half there. So, if we will write this central difference table in Gauss backward difference form, then this table can be written in the form, since we are just approaching here the values like x of -3, x of -2, x of -1, x0, x1, x2, x3, and we are just computing this value at the middle of the table here. Since already we know that the formula, that is a Gauss forward formula which can be used at the beginning of the table, backward formula which can be used at the end of the table. So, that is why we are just trying to evaluate this formula which should be used at the middle of the table here. So, that is why we can just express this tabular values as x0 as in the middle of the table, and all other points preceding and succeeding are in the form of minus and plus form here. So, the corresponding y values or these functional values can be expressed in the form of y0, y of -1, y of -2, y of -3, y1, y2, y3 here. And if you will just use the central difference approximations here, we can just write the central difference approximation as a del of y of -half here and a del of y of 0 half here. So, similarly we can just write del square of y of 0, then del q of y of -half, then del to the power 4 of y0. So, likewise we can just consider these tabular values for the Newton's backward difference. We are just going one step back to evaluate these tabular values there. So, that is why it is called Gauss backward difference formula. And if we will just go forward one step here, then we can just say that that is a Gauss forward difference formula here. So, for the forward difference formula, if you will just go here, so that can be represented in the form of first function is a y0 here, then delta y of half, then we can just go like a del square of y0 here, then we can just go like a del q of y of half here, then del to the power 4 of y0. So, likewise we can just go. So, this is for like a Gauss backward formula. If you will just go for the forward formula here, we can just write Gauss forward formula as that we can just consider this central difference approximation, that is in the form of x of minus 1, x0, x1 here, so y of minus 1, y0, y1 here. So these differences, first we will just go for here delta y of half here, then del square of y0 here, then del q of y of a half here, then del to the power 4 of y0 here. This means that a forward marching step we are just approaching here to get this forward difference formula. So first case we are just telling that p should be lies between minus half to 0 here, and in this case p should be lies between 0 and half here. This is the condition. If we will take the average of these two, so then we can just obtain this Stallings formula, where p should be lies between minus 1 by 4 to 1 by 4 there. And if we will just take this even differences like average of even terms there, then we can just obtain Bessel's formula, where this p value should be lies between minus 1 by 4 to 3 by 2 there. So now we will just go for a complete derivation of this central difference formula. In the Gauss backward difference formula, we can use y0, then its even differences. Even differences, if you will just see, like y0, del square of y0, del to the power 4 of y0, we are just using here. And odd differences of y of minus half. Odd differences means this power, if you will just see here, that is del of y of minus half here, del q of y of minus half here. So likewise, all the even powers y0 we are just using, square here, fourth here, then sixth again. And if you will just go for this odd differences here, so odd differences means it can be taken y of minus a half here, so this is 1 here, then this is 3 here, then again this is 5 there. So likewise it will just continue. And our aim is that for the derivation of this formula, we have to consider yp as in the form of a0, y0, a1 delta y of minus half there, a2 del square y of 0 there, a3 del q of y of minus half plus a4 del to the power 4 of y0. So if we can just express in this form here, then yp can be written as a0, first term we can just write as a0, y0, a1 delta y of minus half here, a2 delta square y0 here, a3 delta q y of minus half here. So likewise we can just express. Since we are just expressing yp as in this form here, if we can just express yp in terms of delta, and if we will just compare both sides the coefficients, we can obtain the values of a0, a1, a2, a3, all these coefficients there. So if we want to compare these coefficients, first we have to express yp in terms of Newton's forward difference formula here. So if we will just express yp in terms of Newton's forward difference formula, we can just write that as e to the power p of y0 here, and which can be written as 1 plus delta whole to the power p of y0 here. And if we will just expand these coefficients in terms of delta here, which can be expressed also in the form of central difference operators, we can just find all other coefficients thereover. So if you will just use this operator, then we can just write that in the form of y0 plus p delta of y0, p into p minus 1 by factorial 2 del square of y0. So likewise we can just write here. So it can also be expressed in the form of like a central difference forms, that is, if you will just write delta e to the power delta y of minus half here, so it can be written as a delta means y of half, we can just write e to the power minus half of y0 there. Then we can just use the central difference operator e to the power half minus e to the power minus half into product of the terms. So if we will just write that one, we can just write that one as 1 plus delta whole to the power p. This can be written as a0 y0 plus a1 delta e power of minus half, a2 delta square of y0 here plus a3 delta e power of delta q of e to the power minus half of y0. So, likewise we can just write, and if you will just try to find this coefficient here, so it can be written as a delta e to the power minus half of y0, so which can be expressed as a e to the power half minus e to the power minus half into e to the power minus half here of y0. And if you will just take this product here, this can be expressed as e minus 1, or if I am just adding it up here, so I can just write e to the power half, this is a 1 minus e inverse of y0 here. Till now we have discussed this Newton's forward difference formula and backward difference formula and the examples based on it, and in this lecture also we have discussed about this central difference operators and in tabular form how it can be related, and in the next lecture we will just continue this Gauss forward difference formula and backward difference formula. Thank you for listening this lecture.